I'm Scott Frye from Agero, and my colleague Kathy Slesnick is going to come up later and talk to you in depth. We're going to talk to you about automobile route matching, which is about seeing how the path that an automobile takes. And we're specifically going to talk about it with an algorithm called dynamic time warping. And Kathy's going to address some of the performance improvements that we realized when we moved the algorithm over to Apache Spark. So your first question is probably, what is Agero? Well, we're a roadside assistance provider. We organize the tow trucks to get to cars that are disabled. We have about 80 million customers. But the main thing is we're obsessed with driver safety, and we're really trying to make sure that we can make the whole driving experience better and safer for the driver. In 2014, according to the National Highway Safety Organization, there was about 100 deaths per day for driving from car accidents. And we're really interested in trying to reduce that. So to address that, we've come up with an innovative mobile application that we call MileUp that does real-time behavior analysis of the driver to look for actionable insights that it can feed back to you to make you a safer driver overall. So here are some of the services that Agero offers. We obviously get the tow trucks to the providers like AAA does and other companies. We do accident scene management, but today we're going to talk about the mobile telematics, which is where we're collecting data from the drivers and applying analytics to it to solve some of these problems that we're interested in. So Agero has, as I said, 80 million customers. We process about 10 million roadside events every year, and about 1 million of those are accidents. So those are the ones that we're focusing on because we're trying to reduce those accidents and make the overall driving experience safer. We operate 24/7. We have 6 different call centers around the country where people will call in when they have a roadside problem, and they'll dispatch a tow truck to address it. And there's a lot of logistics around this, figuring out which tow truck is the best and what kind of car you have and what kind of equipment. So most of it's a manual process, but we're in the process of automating that as well. To process all of this data, we have at Agero 12 full-time data scientists, and we've collected about 3 petabytes of data with our MileUp application, and it's our job. This is some of our data scientists you see here in the picture. They at ODSC earlier this year. But it's our job to analyze all this data and look for patterns in it to try and figure out if you're a safe driver, and if you're not a safe driver, give you some feedback so that we can make you a safer driver. Most of this analysis is done with Python on the AWS platform using lambdas and other offerings of theirs, but we also do a lot of analysis and algorithm development on Spark. We have a wide range of algorithms that we process. There's no time to go into all of them today, but Kathy's going to talk a little bit about the dynamic time warping algorithm and how we applied it to a very specific part of what we do. Our main goal of all of this is to do crash detection and to bring services to stranded drivers. That's what we keep coming back to as our main goals of we're trying to achieve. So this is an example of what our MileUp app looks like on the screen here. If you want some more details about it and how we used AWS to leverage AWS to address some of these, to process some of this data, our Vice President of Mobile Engineering, Raj Behera, has given a talk at the AWS reInvent, and there's a YouTube link there that you can go and see some more details of how the whole crash detection thing works. Because we're not going to go into too much of that today. We're going to focus on the drive routing algorithm. So we released our app last year, well, actually the year before, in 2016. And we had about 1,000 users in the beginning. Luckily, we put a posting on Beer Money Reddit thread advertising the fact that we gave away gift cards for miles because we were trying to collect as much data as possible to analyze. And after we did that, the app became wildly popular, and it went to number 10 on the Apple's lifestyle category page. So it became, an app that everybody wanted. But one of the things that it did allow us to do is to grab all that data that I talked about. So once we got the app up there and we collected data, since we launched it, we now have about 2 billion miles that we can analyze. And 11,000 of those are detected accidents that our application has been able to find that there was an accident with one of our several algorithms. And about 450 of those, we actually have the reports from the insurance companies about the details of the accident. So that gives us invaluable data to be able to figure out, what an accident is, what a severe accident is, and how to determine the difference between the two of them. And the earlier you can detect those accidents, the faster we can get roadside and emergency services to them and hopefully save some lives. Just to give you an idea, oh good, the animation's working. Just to give you an idea of the amount of data we collected, this is the data we collect in one day, and every single dot represents a trip. And this was at the peak when the application was the most popular. So this is a huge amount of data that's coming in that has to be processed in real time. There's no way to do it in a single thread. You definitely need some parallelization here, and that's where Spark and Databricks was very helpful to us. So Kathy's going to come up now, and she's going to talk a little bit about how MileUp works and how we applied this particular algorithm with Spark to our solution.
Thanks, Scott. Right, so how does MileUp work? So MileUp was conceived as a crowdsourcing application to get data for us to develop algorithms to detect crashes. And so it's still available on the App Store today, though we no longer pay people for miles. But our users go download the app. When you start driving, we start collecting data, and we're getting the sensor data from your phone. So GPS, accelerometer, gyro, whatever sensors your phone has. And it goes through a suite of algorithms that we have. Some are machine learning, some are basic statistics. And the original goal was to detect accidents in real time. And the talk that Scott mentioned by Raj Bahar, he actually went through that whole process. It's on YouTube. I encourage you to go look at it if you're interested. I'm going to focus today on the second part, which is detecting driving patterns. So once we had all these data, we thought, we don't want to just detect accidents, and we actually want to start preventing accidents. So what can we do to encourage people to drive more safe, to drive safer? And the hypothesis was if we could start building up patterns of driving behavior and start informing people about their own driving behavior and how that affects your risk for an accident, it would incentivize people to drive better. And so that's what I'm going to talk about today, is that piece of it. So the first thing we thought about in going down this road was, this is a lot of data to process, right? 2 billion miles, 300,000 users, that's several thousand users, or several thousand miles per user. And if I want to build up a driving profile, I want to look at as much of a single user's data as possible. So all of our driving pattern analysis is run on Spark in Databricks. We have a nightly job that kicks off every night, pulls everybody's data from that day, and updates their profile. Here I'm just showing a screenshot of an actual driving profile. If you look at the app, this shows different behaviors and your risk score. So we look at dozens of driving behaviors, way more than I can talk about in a short time today. So I'm going to focus on one that we looked at really early, and that is route familiarity. And what I mean by that is routes that people drive over and over. So this is your daily commute, your drive from your house to your local grocery store. If you have kids like I do, your drive from your house to your kid's school. Roads that you drive all the time that you know. And there have been a lot of studies that show you drive differently on roads that you know very well, that you're familiar with. So in some ways, you drive worse. So people are more likely to speed and to go around corners very aggressively if they know the road really well, because they know how fast they can go, which might be above what the speed limit says. True story, I actually have an uncle in Connecticut who got a speeding ticket going 87 miles per hour on a 35-mile-an-hour country road, and his reasoning was, well, I know the road really well. I drive it at 4:30 a.m. every day when no one's there, and I wanted to get to the train. So definitely people tend to go faster. And then another big issue with driving on roads that you know very well is that you tend to be more distracted. You know the road, you let your mind wander, you're more likely to pick up your phone and look at that text that came in because you don't have to pay attention. And so for that reason, you've probably heard the statistic that most accidents occur within a few miles of a person's house. And in part that's because you're around your house more, but it's also because people are distracted. And so most fender benders happen on roads people are familiar with. They're not paying attention, they don't notice the person in front of them slammed on their brakes, and they bump into them. On the flip side, you are less likely to get into a very severe fatal accident on roads you know very well. So we know in that sense it actually makes you more safe in terms of really severe accidents. So we wanted to look at how often our users were driving on the same roads. The first question was, well, can we even do this? It's a pretty hard problem, right? Comparing data point by point is very expensive. And in addition, even if you could compare data point by point, the same trip from point A to point B, exact same roads, is not going to look the same taken twice, right? You're going to have different velocities. You get stuck in traffic, get stuck at stoplights at different places. So that's a challenge. And also, we didn't want to just identify exactly the same roads. We wanted to identify when you're driving a similar road. Like on my commute home, I can take one of any 3 side streets, but it's basically the same trip. So we have a lot of data to process. So the first thing we looked at was, okay, we definitely need to start by constraining the search space. So the first thing we wanted to do was look at trip endpoints. We knew we needed to run this in parallel. So I did this analysis, and the 2 constraints that I knew I had were I needed to process all of a user's data together. So I couldn't, when I parallelized, I couldn't have part of my trips running on one thread and another part of my trips running on another. I needed to keep all of those together. And then I'm a Python developer, so I wanted to stay in Python and PySpark. I didn't want to have to learn Scala. So what I ended up doing for this first part was to parallelize on the driver. So I made an RDD, a resilient distributed data set, on the driver, and then I mapped that to a pure Python function. And what this function did was it went out to Dynamo on AWS, where we are keeping metadata for our trips, and it pulled the metadata for each trip. And essentially, I was parallelizing that pull because I had parallelized on the users. I pulled back all that data, and I ran clustering algorithms on the start and endpoints of the trips, and I created pairs that had the same start and endpoints for each user. And then I had another set of just statistical algorithms that went through and looked at midpoints and distances and said which trips were the same within those pairs to some threshold. And what it produced was a vector of matched candidate trips. And my original hope was, hey, maybe this would be good enough and I could stop there and I'll have these familiar routes, which of course was not the case. I'm sure you can all think of, and I found several instances where a trip would have the same start, endpoint, approximate midpoint, and distance, but does not go on the same roads at all. But just to give you a snapshot of the processing and analysis at this point, I ran a sample just to give you guys numbers. I took 50,000 users, 2 weeks of data. I threw 112 cores at it, and I was able to run all of this in about an hour. So pretty good. And it produced 400,000 trip pairs from many millions of trips. So I knew that I needed to do something a little bit more sophisticated now with these trip pairs, right? Because it's not possible to go through and look and see which ones worked and which ones didn't. And I landed on an algorithm called dynamic time warping. So before I decide how detailed to get, do we have data scientists in the audience, or is there a lot of data scientists in the audience? Okay. So some of you might be familiar with dynamic time warping. This is an algorithm used in time series analysis. It's used a lot in speech recognition, and it's a way to measure similarity between 2 temporal signals that vary in speed. And so here I've just put up an example of 2 cars. It's probably not obvious from first look, but they're actually traveling the same route. But they started in different places. One of them got stopped at a stoplight and was stationary for a while. The other kept going. Just doing a one-to-one comparison of the distances between the points in these time series is not going to give you a great similarity metric. And so dynamic time warping, what it does is it takes each sequence and maps it to the closest point on the other sequence. And so you can see This algorithm was actually able to tell they started at different times, that sometimes one car stopped and the other didn't, and this is going to give me a much better similarity metric. And so I did this in both latitude and longitude, and then combined the measures. Just one more slide on I'm not going to go into too many details, but the way dynamic time warping works is it creates this nonlinear warping function, which actually maps one into the other. And the issue with dynamic time warping, it's very good, but it's very computationally expensive. Its original instantiation, it's order n squared. So not very easy to run. There have been probably half a dozen theories, methods people have come up with to speed it up. I used one called fast-DTW, which actually iteratively constrains the search pace, samples the data, and goes back and forth and does that. I picked that one because it's pretty good, and also because there was already an open source Python implementation of it I could use. So in thinking through this problem, just for even this subsample that I chose to run for you all, I had 400,000 trip pairs. Order of magnitude calculations here, the average driver commute in the US is 25 minutes, so it's roughly 1,500 data points per trip. We take data at 1 hertz. Running a sample comparison, that's about 5 seconds per match, right? Mapping it out, about 600 hours of compute time. Clearly was going to need to put in some parallelization there. So the first thing I did was just to take the dynamic time working algorithm and put it in the end of my pure Python function, because that's the way I was used to thinking about it. That's the way I'd done the proof of concept. I tried to do that, and it was not working. It was taking forever and ever. And when I went to look at the Spark UI, what I found was that the compute resources were being used completely inefficiently. Because I'd parallelized on the drivers, and drivers had very different numbers of trips. Some of the cores were finishing their processing really fast, and some were going on and on forever. And so this was clearly not the right way to think through parallelizing and running this problem. So I took a step back, and what I ended up doing was running the first part as I had, parallelizing on driver, then coming back and taking that vector of pairs and turning that into a Spark data frame, and then creating a user-defined function to run row by row, the DTW. And that worked an order of magnitude faster. It still wasn't perfect with the cores because different trips have different lengths, but I was able to run it in a reasonable time period that way. And so, and one thing I did want to say, I've listened to some talks this morning about the new Pandas UDFs, which I'm excited about. This was all done before that came out, so it could be a way to speed it up even more using something like that. But so what we learned, so this was really the first analysis, the first crack we did at analyzing driver behavior using Spark. And so it was our learning experience, our first thing, and we learned, hey, we really can look at driving patterns from all this data using Spark, but all of us are Python developers, so we learned our lesson that we had to kind of shift our thinking about how to parallelize, how to run these things. And something I had to go through with trial and error was learning that I didn't have to just think in RDDs or data frames. I could use them strategically at the right time to get the results I wanted. And so for this example, I processed through 600 million points on the 112 cores. It ran in about 5 hours. And here I'm just showing you the full flow through of that process. And so this is now the template that we use for all of our driver behavior analysis of how we think through the analysis. So that's all I had on dynamic time warping. A couple other things I did want to say is that if you're interested in the MyLab app, I would encourage you to download it. As I said, the sweepstakes, the paying you for data part is sunsetted, which you will see the reviews went down when we stopped giving away money. But we do still do the driver behavior scoring, and we have a great beta out right now where it's actually automatically patched into our emergency response centers. And if the app detects you're in an accident, they will actually call you to see if you need emergency services, and if they can't reach you, they will just send emergency services. So that's a pretty cool feature, and if you're interested in that beta, you can email either Scott or myself, and we can put you in the list for that, even though it's not publicly available right now. Yeah, so questions? I'm sorry, I can't hear you. The code that I ran? It's not open sourced. It's all I use the FastDW was an open source library, and I can give you the link to that. It's actually in the slides, the link to that. So that's open source. My implementation of it is not.